Hello class, I'm going to walk through the week 6 solutions for our homework assignment. Define each term, so the multiplier, I defined it this way. It's one of the two factors in the multiplication operation. It's the factor that represents the number of copies of some amount of stuff. And I also mentioned here that we will use the first factor in the operation of multiplication as the multiplier. That'll be our default assumption. Now you might have defined this differently. As long as you capture the essence of what I wrote there, then I think you will have defined it well enough. Multiplicand, one of the two factors in the multiplication operation. This one is the amount of stuff per copy. And we will use the second factor in the operation of multiplication as the multiplicand. The product is the result of the multiplication operation. It's the amount of stuff when some number of copies of some amount of stuff per copy are combined together. Sometimes people will say it's the total amount, but you're going to see down the road that I don't really like calling it the total amount of stuff. When we start multiplying by fractions, the word total starts to feel maybe a little bit off. We'll talk more about that later. Partitive division is the operation that determines the amount of stuff per copy, such that some given number of copies combines to make a known amount of stuff. Partitive division is the operation that solves essentially a missing multiplicand task. You're trying to find the amount per copy. And quotative division is the operation that determines the number of copies of a known amount of stuff per copy that combine to make some other amount of stuff. And so it solves a missing multiplier task. It's in short, it's finding the number of copies, whereas partitive division is finding the amount per copy. Number 2, invent a task that is resolved by solving the following numerical operation. And then there are a bunch of instructions here. So this actually is a pretty simple task here. 8 times 3, I just said, hey, Sue gives 3 candies to each of 8 friends. How many candies did she give away? I am assuming that the 8 needs to be the multiplier. So this would not have worked if I had said, Sue gives 8 candies to 3 friends. How many candies did she give away? Because then it would have been 3 friends times 8 candies per friend, and 3 would have been the multiplier. So I had to have the 3 be the amount of candies per friend, and the 8 be the number of friends, which is an example of what it means to like have an amount of copies. Each friend is a copy. And then solve the task and put an appropriate referent on the product. And so the answer is 24 total candies. And it's always good to answer questions with complete sentences. I didn't do that here, but I would have said something like Sue gave 24 candies in total away, or she gave 24 candies away to her friends, or something like that. And then here was just, I didn't ask for a visual, but I made a visual anyway. Each box represented a friend. So I had 8 boxes and 8 friends, and there were 3 candies, right? 3 dots in each box. And this represents this notion of 8 copies of 3, where 8 is the multiplier and 3 is the multiplicand. Number 3, model the operation below using a grid and determine the product. So I interpreted the 5 as the number of rows and the 9 as the number of columns and made this grid. And we have if you were to count them out, right, if you zoom in here and just start counting these 1, 2, 3, etc., you would get up to 45. And so we have 45 little boxes in there. And then use the grid to demonstrate that multiplication is numerically commutative. So I actually pull apart the grid in multiple ways. I pull it apart in such a way that I'm looking at the rows, and I am thinking of the 5 as the multiplier, the 9 is the number of stuff per copy. So each row is like a copy, and there's 9 boxes per copy, and that gives me a total of 45 boxes. But if you flip that around, split the box or split the grid apart into columns, you can see that we have 9 copies of something. And so each column is a copy. We have 9 columns times 5 boxes per column. That also gives us 45 boxes. So the grid is a really nice way you can pull the grid apart by columns or by rows, and it just shows that numerically 9 copies of 5 versus 5 copies of 9 that yields the same result. This is the same grid that we're starting with. Use the grid you made above to justify the distributive property. So we have this notion that 5 times, and then a sum, 3 plus 6, equals 5 times 3 plus 5 times 6. You can do what we call distributing, multiply the 5 times the 3 and the 5 times the 6, and then add the results together. And the grid is a very helpful way in seeing why that works, especially with addition. If I take 5 times 9, and I decompose 9 into 3 and 6, like I did here, you can see this is just equivalent to breaking this grid apart in such a way that you have 6 columns for one part and 3 columns for the other part. And you can see that if I do 5 times 6, I get this part of the grid, and 5 times 3, I get that part of the grid. And so together it should make sense that it's the same thing as 5 times 9. Okay, number 4. I'm sorry for that noise. Number 4, calculate the following operation in 3 different ways, one of which should be by using the standard algorithm. Also make sure that you use decomposition at once and indicate where you used it. All right, so I used it right away. I decided I'm going to decompose 21 into 20 plus 1. And then I used the distributive property next. So the 39 distributes. And then I had 39 times 20. I could have done some more decomposition here, but I just went ahead and multiplied 39 and 20. You know, you could do something like 20 30s plus 29s, or there's a variety of ways you could do decomposition. You could do 10 39s plus 10 more 39s. So many ways to do this. You could decompose, you know, that number or that number and then distribute again. You choose. And then plus one copy of 39. So this should make sense to you that if you're doing 20, if you look at this in the commutative sense, so think of 20 plus 1 as the number of copies. You could think of this as 21 copies of 39. I know we're defaulting to interpreting the first number as the number of copies, but you could invoke the commutative property and do this, and then break, and then do the decomposition, and so interpret all these as copies. So you have 21 copies of 39, so that makes sense that if you combine 21 copies of something together, you can do that by taking 20 of them and then putting one more copy. Right, so it's kind of what you're seeing here, 20 copies of 39 and 1 copy of 39, but of course these are written backwards. I will tend, when I see this statement, I will tend to always assume that the first number is the number of copies, but sometimes mentally we are able to just flip that around because of the commutative property and now think of the second number as the number of copies. But it's in our best interest, in my opinion, to come up with a default assumption that the first number is the number of copies, unless otherwise stated. Anyway, so you get 780 plus 39, and that gives us this 819. In the next example, I decompose the 39 in a way of thinking it, hey, it's close to 40, so I'm going to call it 40 minus 1. And the distributive property applies even for subtraction, so you can distribute the 21. And then we wind up doing 40 times 21 minus 121. So if you want 39 21s, it makes sense that you could start with 40 of them and then just remove one of them. And that would get you down to, 39 21s. And so I did 40 21s, that's 840, and take away 121 from that. That also gives me 819. And then finally the algorithm. I'm going to talk my way through the algorithm. The algorithm is a summary of just a bunch of decomposition. I'm really breaking 21 into 20 and 1, and I'm going to multiply 1 by 39 first. So we do one copy of 39 is 39. And then I'm effectively going to decompose 39 into 30 and 9. And this 2 right here is 20. So I'm going to do 20 times 9. 20 nines is 180. And I believe the algorithm teaches us to do the following. We do 2 times 9 and get 18. We put the 8 under the 2 and carry the 1. But you could really just do this instead as well. I mean, recognize that this 2 stands for 20. And you're doing 20 times 9, and you're getting 180. Just put that there. and then do 20 times 30. That's 600. So you could make three numbers that you're stacked together. Notice how we're just doing, we're sort of treating the number down here as the multiplier, and we're decomposing it and saying 21 39s. Okay, well that's the same thing as doing 139, and then plus 20 39s. But I'm going to decompose 39 into 30 and 9, so I do 29s and then 20 30s. And I get all these pieces that I just add together. Now, the algorithm doesn't teach us to do it this way. The standard algorithm, anyway. It teaches us to say, you know, do 2 times 9 and get 18. Put the 8 there, carry the 1. Then 2 times 3 is 6, and then add that 1, and you get 7. And then you just add these up vertically, so the 9 just drops. The 3 and the 8 combine to be 11, which you put a 1 here, carry a 1, and then add those. It all feels very magical when you just think that these are all single-digit numbers being placed in random positions, and sometimes you carry things and sometimes you don't. I really don't like the standard algorithm. I mean, yes, it might be considered to be proficient, but I like using an algorithm that mimics the reality that we're just doing decompositions. I'm doing 139, and then 29s, and then 20 30s, and then add these up. And notice I'm not saying 2 times 3, I'm saying 20 30s. I'm using words that that remind us of the true meaning of the 2 and 3 in their respective place values. And 30 plus 80 is 110. So you could just do, you know, you carry the 1, do that process, we get 8 here. 819 is the end result, using the standard algorithm, or at least a version of the standard algorithm. Number 5, invent a task that would elicit partitive meaning. So partitive is when we're trying to find a missing multiplicand. It's always helpful to remember that partitive is missing multiplicand and quotative is missing multiplier. So when I see these numbers here, it's 35 divided by 7, I want the 7 to be the multiplier, and I don't know the multiplicand. So this is the structure that I interpret. I'm trying to find that missing multiplicand. So I've got 7 is the number of copies, and 35 is the resulting amount of the product. So this really boils down to the question. By this, I mean the statement here is 7 copies of what make 35? Okay, so this sometimes takes a little bit of practice to make sure you phrase your questions well so that it implies a missing multiplicand task. But I went with Bill worked 7 hours and made $35. How much did he make each hour? So each hour is like a copy. So we're trying to say, hey, 7 copies of what make 35? So there's several ways to do this. You could take the 35 and we'll say $35, and you could write out $35, something like this, and say, okay, I've got $35 total. You can do dots to represent the dollars. You could use numerals to represent certain amounts of the dollars, but we're trying to place them fairly into these boxes so that they evenly spread out. I don't know if I've got $35 here yet. 1, 2, 3, 4, 5, 6. Is that $35? I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's $10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's another 10. I have 1, 2, 3, 4. Am I counting this right? I have $29. How did I get to that? Here's a group of 5, second group of 5, third group of 5, fourth group of 5, fifth group of 5, sixth group of 5. I think I need one more. Anyway, you get the idea. I got all these dollars. Okay, and then you just do this notion of, well, it's going to start placing the dollars, making sure they're being shared evenly. Oops. And Anyway, I'm spending too much time just trying to do a visual here. You want to get these dollars into all these boxes, and the goal is to, in the end, you're going to realize that there should be $5 in each box. And if you do it that way, then you have found the amount of dollars. Sorry for the noise. The amount of dollars per box is going to be 5. And so that means that each box represented an hour. And so 7 hours times $5 per hour will give the $35. So here's our complete structure. 7 hours times $5 per hour gives us the total of $35 made. But you'll notice that it was the 7 hours was the multiplier in this case, and it was the amount of dollars per hour that we were after. So that's a missing multiplicand task, which means that partitive division resolves it. So we would say, therefore, 35 divided by 7 yields 5. Okay, that's the sort of the quotative. So we have 35 divided by 7, so the same operation, but we want a quotative meaning this time. Well, we want to interpret, for quotative division, we need to create a missing multiplier task. So we want a structure something like this. We want to answer this kind of question. How many copies of 7 make 35? And so we could do something similar with making money and a certain amount, but this time the 7 is a known amount, and it's a multiplicand. So that's an amount of stuff per unit of something else. Amount of stuff per copy. So 7 would be the dollars per hour. And we're looking for how many hours. And so I said June makes $7 an hour and earned $35. How many hours did she work? Okay, I was just double checking, making sure that we didn't have to state any assumptions. Of course, some assumptions that we are making here is that he makes the same amount per hour, right? That was an assumption we made. And down here, we're going to, I guess, make that same assumption that the number of dollars per hour remains constant. That is not changing. Okay, so now we have a total of $35, and here they are. I made all the dollar signs earlier. And we are trying to ask ourselves how many copies of $7 per hour will make this 35. So you just got to group them in groups of 7. So 1, 2, 3, 4, 5, 6, 7. So there's 1 hour. Right? It's $7 per hour. 1, 2, 3, 4, 5, 6, 7. There's another hour. 1, 2, 3, 4, 5, 6, 7. A third hour. 1, 2, 3, 4, 5, 6, 7. I think right there. A fourth hour. And 1, 2, 3, 4, 5, 6, 7. And a fifth hour. So we've come to the conclusion that 5 hours of work times making $7 each hour will yield a result of $35 earned. Number 6 here, calculate the following operation using a partitive meaning for division, and then again using a quotative meaning for division. Okay, so with partitive meaning that the divisor is this position here. Remember, we use these words that this is called the dividend, this is the divisor, and the quotient is the result. But when you're doing partitive division, you should always interpret the divisor as the number of copies. So this is, the number of copies is known, but we're trying to figure out is the amount per stuff, which is the multiplicand. Partitive division is a missing multiplicand. It's when you divide the dividend by the number of copies. That's why it's called the fair sharing, because you can think of each copy as like being a child and you're trying to share 204 things with 6 children or something like that. So you have this fair sharing notion. And we're going to do this more numerically. Instead of drawing 204 little boxes to represent whatever these are, notice there's no word problem here. We're just trying to model this, but we're trying to answer this question. 6 copies of what make 204? And I'm just going to break up 204 into, I don't know, 20s. I'm going to put 20 in each box and to see where that leaves us. All right, if I've put 20 into each copy so far, that means I've used up 120, so I keep track of how much I still have left. So remove 120 from 204. That ultimately, is going to take us to 100 or 84. And then I say, okay, I can put another 10 in each safely, because that only will make up, that will get us to 60. So take 60 away from that. That takes it down to 24. And then you might see, okay, now I can put, I think, 4 more in each box. And I get everything used up, and then minus 24. So that should account for all 204. Right, we had 6 30s, that's 180, and 6 4s, that's 280. So yeah, 204 total. But now you can see, because of the fair sharing, we've determined how much there is per copy. So we've answered the what. 6 copies of what make 204? Well, how much stuff there is in each copy is the answer to this question. And so there are 34 per copy. And notice there's no context here. So I don't know, 34 what? 34 something per copy. So we're working pretty abstractly here, but we're still thinking of 6 as the number of copies, and the 34 is the amount of stuff per copy, and the 204 is the resulting amount of stuff. We just don't have a context to be more precise. For the quotative meaning for the same operation, we are doing the 204 divided by 6. We want to interpret the 6 as the amount per copy, and we're trying to figure out how many copies. So like, how many copies of 6 make 204? Okay, we're going to construct this little by little. Let's do 10 copies of 6. That makes 60. We're trying to make 204, so let's do another 10 copies of 6, like whatever 6 looks like. That makes another 60. So we're at 120. Let's keep this up. Another 10 copies of 6. Make another 60, so we're at 180. And then we need, we're down to 24 left. And so we need another 4 copies of 6 to get the last 24. And so then we have a total, I see, thus 34. Notice I'm putting the multipliers in front of the 6's, and maybe I don't need to put the 6's in boxes or anything, but we were trying to find number of copies, and I did this piece by piece. I said, well, 10 copies of 6 make 60, and just repeated that until I got close to 204, and then say, okay, well, how many more copies of 6 do I need? And I was able to do this and determine that 34 copies of 6 will make 204. And here we did 6 copies of 34 per copy make 204. Right, so the answer was 34 in both cases, but the interpretation is very different, right? In the partitive case, the 34 that we determined through division was how much stuff there was per copy, and then the 34 in the quotative case was how many copies there were. And then the algorithm. Now the algorithm very largely mimics this quotative meaning. You just, when you say, hey, does 6 go into 2? No. Okay, then look at this as 20, which is really not 20, but 200. And you say, does 6 go into 20? The answer is yes, so people put a 3 here. But in reality, they're putting a 30. We're just not taught to think that way sometimes when we do this. And we do 3 times 6, and we write 18 under the 20. But really what we did was 30 times 6, and we get 180. So I really just did all of this chunk up front. I said 36's get us close to 200. It gets us to 180, and then remove 180 from 200, and we get 24 still. But we're taught not to put the 0 here, not to put the 0 here, and to think 20 minus 18, and to get just 2, and then just magically bring the 4 down. It feels very, it's very unsatisfying to do the algorithm in the traditional way where everything is, all these place values are not really thought about appropriately. And I'm going to go ahead and finish the algorithm, even though I don't like it. We do 3 times 6, get 18, remove it from 20, get 2, and then bring the 4 down, and then repeat 6 times what? We put a 4 here, and 4 times 6 is 24, and then we subtract, and we say, okay, we're done, 0. The answer is 34. Yes, this worked. But I prefer the version of the algorithm that looks, more like this. Let's get rid of all that. Let me bring this down slightly. We say, and you don't even have to do 30. You could say, hey, let's see what 26s does. 20 times 6 is 120, and subtract that from 204, and that still gives us 84. You say, oh, look, I can do 10 more 6s and get 60, and subtract, you get 24. And you say, oh, 4 more 6s will do the trick. And then you just combine those together. It's very similar to what you saw us doing right here. And this version of the algorithm I like better. You're just stacking numbers and then combining them. Or you can do a little more efficient version of the algorithm and say, well, 36s will get us close. 36s is 180. Remove that's 24, and then I just need 4 more left. And 4 times 6 is 24, and that takes care of everything. And then we can see, okay, 34 6s. 34 copies of 6 is... when I did the algorithm, by the way, you can tell what the flavor was. I was doing a quotative flavor. I was just trying to figure out how many 6s go into 204. How many 6s make 204. Okay, and then this, I think, is the last task. Each task suggests a multiplicative relationship. This is very similar to a task in the lecture. A math class has 24 students, and tables can seat 4 students at a time. How many tables are needed to seat all the students at the same time? Okay, so this, when you have, we're trying to figure out how many tables, each table can seat, 4 people. And so when you're doing this, you're effectively trying to figure out how many copies of 4 will make 24. Right? When you're trying to figure out how many tables you need, each table is a copy of 4, so you're answering how many copies of 4 make 24. And that is a missing multiplier situation, because we're saying how many copies, each copy is going to be a table. We know the amount of students per table, and we know the total amount of students that we want, so we're missing the multiplier. This suggests that we're doing a quotative division, meaning. And quotative division meaning of division, this doesn't ask us to model this. We do 24 students divided by 4 students per table, and that gives us a total of 6 tables. And there was nothing in our instructions here to draw a picture of this, just to identify it as a missing multiplier, missing multiplicand, or missing product task, and then to identify which operation will resolve it, and then resolve it and put the correct units, and state any assumptions we had to make. Okay, so 6 tables is the answer, and here's my division statement that solves the task with all the units in place. And the assumptions we made, of course, was that all tables are the same, that each one is 4 students per table. Because if there's a variety of different kinds of tables, then we're going to have to resolve this differently. Juliet earned $20 in a week watching the neighbor's cat. How much money would she make if she watched the cat for 6 weeks? Okay, so we know the number of weeks. We know how much she makes per week. Well, this is a missing product task, because we know the multiplier and the multiplicand. We don't know the product. And so we just use multiplication to do it. We do 6 weeks times $20 per week. It gives us $120. And of course, we are assuming that her weekly rate does not change. Notice she just says that once she made $20 a week watching the neighbor's cat. So we make the assumption that that will continue at the same rate over the 6 weeks. And the last one, there are 72 cups of water in a large bucket. Daniel emptied the bucket using 9 scoops. How much water did he remove with each scoop? All right, so each scoop is a multiplier, and we don't know how many cups per scoop. That's the missing part. But we know that the total needs to be 72 scoops. And so this is clearly a missing multiplicand task. We're trying to find the amount per scoop. Whenever you know you're trying to find an amount per something, amount of one thing per something else, then that's a good indication you're missing a multiplicand. which means partitive division is the correct flavor of division. You're dividing 72 cups by 9 scoops to get 8 cups per scoop. That's an example of partitive division. Define the amount of stuff per unit, the amount of cups per scoop, in other words, and the assumption we're making here is that all the scoops removed equal amounts. It's not like you had a very large scoop and some scoops maybe had more and some had less, and in the end he emptied it using 9 scoops. So we were assuming that each scoop removed an equal amount of stuff. Okay, and there's our solutions.